Thank you for the opportunity to present to you today. My name is Sarah Haigh. I'm at the University of Nevada, Reno. I'm going to be talking to you today about a series of studies that we've been doing focusing on visual discomfort, electrophysiology, and chrominance. Happy to take questions at any time during this conference, but if you want to contact me via email, you can see my email address here. I'm happy to chat after the conference too. Okay, so we know a fair amount about the different parameters of visual stimuli that can evoke visual discomfort, particularly in the luminance domain. So there are certain spatial characteristics that are common in natural environments, and when these parameters are violated in some way, then they tend to be more uncomfortable. So for example, there's a one-upon-F relationship between spatial frequency and contrast. And when this relationship or this slope is too steep or too shallow, or if there is excess contrast at mid-range spatial frequencies, as commonly seen in stripe patterns, like blocks of text, these images tend to be more uncomfortable to look at. But this is in the luminance domain. What happens to color? What happens in the color domain? Can we find a parameter of color that can help us predict visual discomfort? And so a lot of this work originated from an incident that occurred in '97, where an episode of Pokemon was aired in Japan, and there was a scene that contained a background that alternated at 10 hertz between red and blue. It resulted in over 700 children and adults being hospitalized with seizures. And so this resulted in a series of studies being conducted to look at what was going on in the color domain when with relation to evoking photosensitive seizures in certain patients. So here's the results of one particular study by Para, where they found that white flicker in general, as we all know, tends to be more likely to induce photoparoxysmal EEG activity in patients with photosensitive epilepsy. But surprisingly, blue-red alternating flicker tended to be one of the most noxious stimuli for evoking seizure activity in these patients. And so this got us to thinking, what if there was something about the color differences between the colors themselves that is driving some of these clinical responses? So what we looked at here was the Euclidean distance between different colors in a particular color space. So here we focused on the CIE LUV color space. We plotted the individual colors and then looked at the chromaticity separation, or the distance between these two colors. And so when we replotted Para's photoparoxysmal activity data, we found that the greater the chromaticity separation, the greater the likelihood of inducing a photoparoxysmal response, the higher the number of patients that showed a photoparoxysmal response, and the higher the number of photoparoxysmal responses across all patients. And so it seems that chromaticity separation can explain a fair amount of the epilepsy data in this particular study, at least when we're comparing alternating colors in flicker stimuli. So then that led us to the question, well, perhaps chromaticity separation could be used as an effective parameter for predicting visual discomfort. And so to kind of illustrate this idea, here's a painting by Debbie Ailes, who is someone who experiences migraine with aura, and she chose to adapt one of her previous paintings of a house to represent what she sees during an aura. So you can see there's a lot of block colors used here, neighboring high contrasts. And so this got us to thinking a little bit more about maybe there's something about the difference between colors, this sort of chromatic contrast that could be driving some of the visual discomfort. So what I'm going to be talking to you today is about a series of studies that have been going on for the last few years, where we are looking at the effects of chromaticity separation on behavioral discomfort, and then the impact of the chromaticity separation on neural responses. We specifically looked using electroencephalography, or EEG, And I'm going to show you a couple of experiments looking at first the alpha suppression, which can index cortical excitability and that we can pick up in the EEG. And then 2 studies where we evoked a response using these chromaticity separation stimuli. And then finally comparing the evoked response in a visually sensitive group, in this case, individuals with migraine, compared to headache-free individuals, to see if we can start to map what's going on neurally with increased chromaticity separation that could be related to the discomfort. Okay, so first we started with a behavioral paradigm, very simple. We took color pairs, paired them together in these striped patterns, and then asked participants to rate them on how uncomfortable they were to view. The rating scale went between 1 and 10. I'm just showing you 1 and 6 for simplicity here. 1 being that's fine to look at, and whereas 10 was horrible, please take it off the screen as soon as possible. And so participants saw these stimuli 1 by 1 and just rated them on 1 to 10 on how uncomfortable they were to look at. So once they responded, then a new pattern appeared. We used different color combinations as well as chromaticity separations to prevent the participants from being able to track the chrominance as their possible metric for consciously rating these stimuli. And so to kind of throw participants off the track a little, we had lots of different color combinations. Again, though, we just asked them to rate them on how uncomfortable they were to look at, and continued on. And so here I'm showing you one of several experiments that we ran in this one single paper, where we plotted discomfort as a function of the chromaticity separation. And here I'm showing you one experiment where we compared red-blue, green-blue, and green-red color pairs and manipulated the chromaticity separation. We did this so that we could cover the extremes of the screen gamut. And I'm going to be constantly using these 3 color pairs as a little bit of consistency across the different experiments. So we'll see this again and again. But what you can see is that regardless of the color pairs used, we can see that the greater the chromaticity separation, the greater the discomfort evoked. And so from here, we decided to work out what was going on in visual cortex by looking at the neural response in EEG. So again, we used 3 color pairs, so red, green, green, blue, and blue, red, to cover the extremes of the screen gamut, and then increase the chromaticity separation from small, medium, and large, so that we had these 9 stimuli. We reduced the number of chromaticity separations and the number of color pairs that we used so that we can maximize the number of presentations for the EEG experiment, so we could stabilize that EEG response. So first we looked at alpha power, and so greater alpha suppression is associated with increased cortical excitation. So the more excitable a cortex is or is becoming, the greater the alpha suppression. We also looked at posterior electrodes over visual cortex, so O1, OZ, O2, and compared those to electrodes that were covering the front of the head, so FP1, FPZ, and FP2, to see if any effect of chromaticity separation was systemic across the cortex, or whether it was something that was more likely to be linked to just visual cortex. So what we can see here is that regardless of the color pairs used, the greater the chromaticity separation, the greater the alpha suppression, and this was only seen in posterior electrodes over visual cortex and not in frontal electrodes, suggesting it is a purely visual phenomenon. Next, we wanted to evoke a response in visual cortex, and we decided to use steady state visual evoked potentials because they are very high signal, relatively low noise, and we can also manipulate the temporal frequency so we can do some more sophisticated work with it. So on the left here, you can see 2 different temporal frequencies, and we see that very clearly in the ERP. And then when we transform this into frequency space, we can plot the power at each of these frequencies to identify the power evoked at different chromaticity separations. So in this exact example, or the study that we used, we presented the stimuli at 5 Hertz, where we had the grating pattern alternate with a gray screen at 5 Hertz so that we can measure the evoked power. We can see that the larger the chromaticity separation, the greater the power evoked at 5 Hertz. So the black is the largest chromaticity separation, and the green is the smallest chromaticity separation. And this was consistent across the different color pairs that we used. Finally, then we looked at, so then we also looked at the reports of visual discomfort evoked from these stimuli in these same participants. And we can see on the right here that the greater the chromaticity separation, the greater the discomfort, again, replicating what we've seen before, and that we can see that those trends are pretty similar when we change the y-axis for the mean 5 Hertz amplitude evoked. You might also be able to see that there are some color-specific effects here. So blue-green color pairs tend to be rated as more comfortable and evoke less ERP power or power in the EEG. And that seems to be very consistent across all of our studies. So there might be some color-specific effects, but even across the different color pairs, we're still seeing that chromaticity separation drives the majority of the variance here. Okay, so finally, we then looked at the event-related potentials to these same stimuli, but wanted to compare individuals who had migraine compared to headache-free individuals to see if those who are visually sensitive show a greater effect of chromaticity separation in their neural responses and in their behavioral responses compared to a less visually sensitive population. And so we can see in headache-free individuals on the left and migraine on the right, that both groups produced a larger N1 here, if you can see my cursor, produced a larger N1 to the largest chromaticity separation, and that N1 amplitude tended to decrease with smaller chromaticity separations. Now, when we replot the amplitude of this negativity here, and then compare it directly between headache-free and migraine individuals, we can see that the larger the chromaticity separation, the greater the N1 amplitude, particularly in migraine, and particularly in occipital parietal electrodes. And so again, we're replicating that the greater the chromaticity separation, the greater the neural response, but we're also now showing that those who are visually sensitive tend to be even more sensitive, tend to produce an even larger neural response to these stimuli compared to a less visually sensitive population. Should also note that ratings of discomfort were recorded for all participants. And once again, we found that there was an increase in discomfort with chromaticity separation. This was true in migraine and in the headache-free individuals, but the individuals with migraine reported greater discomfort for all chromaticity separations compared to headache-free individuals. So again, we're finding that the same effects of chromaticity separation in visually sensitive and non-visually sensitive populations. We're just finding more sensitivity or greater sensitivity in the visually sensitive populations, as would be expected. So hopefully by now I've convinced you that chromaticity separation drives discomfort and a larger neural response. Those who are visually sensitive, so those who have migraine in particular, report greater discomfort and greater neural responses compared to non-sensitive individuals, which is consistent with the effects of luminance that I reported at the beginning of this talk. Now, we've been plotting the chromaticity separation so far in a perceptual color space. We have also plotted it in terms of cone activation. And we do find similar effects, but these effects tend to be weaker across the board. And so is there something specific about the perceptual color space that is closer related to our perceptual visual discomfort? If so, then that means we have to have something relevant for the biology, okay? We are working with the theory currently that the greater discomfort is a homeostatic response to help the individual reduce the heightened neural excitation So by avoiding these stimuli, it's less metabolically demanding on the system. However, for all of this to be true, we have to find a perceptual color space in the visual system that maps on quite nicely so that this theory holds true. So we can draw on some data by Brewer and Haigh, who found that when they mapped color space in V4, that the way that it was oriented sort of followed something similar to a perceptual color space that we've been reporting before. And so we can see that V4 might actually have this perceptual color space. And so if large chromaticity separations are activating disparate parts of the cortex, perhaps local inhibitory mechanisms are struggling to keep the excitation under control. This is driving, or at least related to the discomfort. And so this could be why large chromaticity separations in particular are uncomfortable and evoke greater excitability. Okay, so lots of people to thank. Thank you for your attention. If you have any questions, please let me know. And thank you for listening.